So, welcome to this lecture on dynamics in mechanics and biology, a lecture in a course on industrial mathematics and computation. So, there are three topics that I would like to introduce today. The first topic is to apply a numerical solver to compute solution trajectories of ordinary differential equations. In the second part of this lecture, I will we will do a case analysis of the parameters in an ordinary differential equation. This equation models damped harmonic motion. So think of a car suspension mechanism. In the third part, I will give a very brief introduction to how ordinary differential equations arise in mathematical biology. And we will arrive to the notion of catastrophic jumps and hysteresis. So the subject of ordinary differential equations, even when one considers a simple first order differential equation, that can already lead to some very interesting results. Okay, but let us begin with the beginning. So I will start with the planar pendulum that I will use as an example to solve numerically a differential equation. So here is the model. So in order to solve this numerically, we will have to introduce a new variable to reduce the second order differential equation to a system of two first order differential equations. Now, what does this problem here define? So the solution or the equation defines the behavior of a planar pendulum. So what do we consider? We have a mass suspended on a rod, and we consider the deviation from the equilibrium. So the equilibrium is when the angle is 0. So the angle theta here is taken to be initially to be pi over 6, and there is no initial velocity. So the problem that we are going to solve is an initial value problem. So the system itself involves the length. So we derived the equation in the last lecture, but we can reduce this to one parameter. So the mass drops out, as we have seen last time, the gravitational constant over the length of the rod or the string to which the mass is attached. That length and the gravitational constant, they can be lumped into one constant alpha. And if we like, we can take this alpha equal to 1. Okay, so what is the auxiliary variable now? Well, that is the velocity. So it is the change in the displacement over time. So then the original equation is written as the derivative of the velocity that equals the right hand side, and then the equation that we add describes the relation between the displacement and the velocity, stating that the derivative of the displacement is the velocity. That's a classical example, and it appears in the tutorial of this package differential equation, which is an alternative to what we have used in a previous course in numerical analysis, the SciPy ODE int from ODE pack. So here in this course we kind of favor more Julia, so let's use a pure Julia package. So here is the reference, so it's a fairly recent package. And in order to use this numerical solver, we have to define a right-hand side function. So here I do this rather pedantically with a very long documentation string. So this is a function that is going to change its first argument, so therefore the exclamation point that's added to it. So the left-hand side is the first argument. So we actually assign what is the right-hand side to the left-hand side. So the solver is set up to solve systems. So one provides a second argument, the original variables in the system. So here this will be the angle and the velocity. The third argument are the parameters. So here we have only one parameter, alpha, and then time is the independent variable, the last variable. So in defining this right-hand side function, we can, instead of writing u1 and u2, we can unpack the components of the u as the angle and the velocity, respectively the first and the second component. Okay, so that's the right hand side. In a way, if you ever used SymPy, the SciPy module of ODE int, that is a very similar approach here. The syntax is only different. We define the initial conditions, we put them in an array. We then have to define the time span and set the value for the parameter. So with these three things done, we then define the problem as an ODE problem, ODE for ordinary differential equation. We have then the problem defined, not yet solved. So that comes next. Then we solve it. If everything goes well, we see also some numbers appearing, but the numbers, let's not look at them now. Let's plot the solution trajectory. So we plot both the displacement and the velocity in the same figure window, 2 rows, 1 column. And the labels are the angle, theta, and the velocity. The horizontal axis is time. Here we see the solution. So we have a pendulum that represents a perpetual motion. So we have a very nice perpetual, very nice periodic function. So in the first plot we have the angle theta, and then one can see the corresponding velocity. So when the velocity is negative, that means that we go in the opposite direction of the displacement. And you can see that when the angle is at its peak, if we are at the maximum deviation from equilibrium, then the velocity is actually also starting to go negative. So we have inflection points. Here you can see this when we reach at the other side. So the velocity then turns from negative to positive, and then our pendulum swings in the other direction. So whenever there is an inflection point with the velocity, we have a peak or a valley in the displacement angle. So even by not looking at the numerical quality of the solution, so this is not a course on numerical analysis, so we are mainly focused here on interpreting the results and formulating the problems. We trust that the solvers will be fine, and the interpretation of the result is mainly geared at verifying whether our model makes sense. Okay, so this was an unrealistic model because there is always friction. There is the air resistance, for example, so there is a damping. So we consider damping, not yet forcing here, that's the next slide. So we have an extra term, so the damping is proportional to the velocity. So the higher the velocity, the stronger the damping. So the purpose of this exercise is to define the problem and then to solve it. So in a way, this looks like a very straightforward exercise, but please do it because once an exam comes up and you have never used the technology to solve a differential equation, it will be a difficult question then, and you will run out of time. So please try to do this exercise. Now the second exercise is when there is not only damping but there is forcing. That means that there is, it's like when a child is sitting on a swing, you kind of push, you give it a push to keep the swing going. So now there is another constant. So I have not honestly tried these constants. I trust that they are fine. So it's better probably to think about a pendulum. If something swings too hard, then no harm being done. But the purpose of exercises 1 and 2 is that you get familiar with a numerical solver. Okay, so let's look at a model from mechanics. So let's look at an ordinary differential equation which models damped harmonic motion. So that's the equation for damped harmonic motion, and this models a suspension mechanism. So we write this with two parameters. The first parameter is zeta, and the other parameter is omega. So from strictly sense, if we look at this equation, we don't really care. We could have called them A and B our parameters, but it will turn out that these parameters have meaning. So writing it in this way already reveals something if we look to the symbolic solution. So this is an equation that essentially reduces to a quadric, and you can recognize the quadric if you kind of denote the derivative by d, and d to the power 0 is 1, so there is a derivative operator. Then the equation that corresponds to this differential equation is 1 plus 2 times zeta w plus omega to the power 2. So there is this factorization that goes in, and the characteristic equation of the differential equation, when this gets factored, you have the two roots, and whether you have real roots or complex roots, and the real roots will be for the damping, the complex roots will be for the oscillation. I hope I don't say this wrong here, but the importance of this engineering notation is that we recognize the already the critical values of the parameter zeta will be 1. That will be the critical parameter. So if it's less than 1 and larger than 1, the solution will fundamentally differ. So there is a whole family of solutions if we do not specify the initial conditions. So we have two parameters, C1 and C2. They are determined if we say we give an initial displacement and an initial velocity of 0. Imagine this is a suspension mechanism. You're driving a car and Chicago is full of potholes. So you bump with your car in a pothole, and then what happens to your car? So your car has dampers that kind of absorb the shock that you would otherwise feel a lot harder when you hit a pothole. Okay, what can happen? Okay, so there is a Jupyter notebook also posted for this. We did a lot of symbolic solving in the previous lecture, so here I will not drag you through the specifics of how the solution was computed. See the posted notebook. But here you see the case when zeta is less than 1. So remember we had zeta square minus 1. And here is actually the interesting periodic solution. Now, of course, if you are considering a suspension mechanism, so this is when you hit a pothole, and rather than immediately going back to the original state, your car actually oscillates up and down. So several blocks further, you're still kind of shaking through this effect of the pothole. So that's actually not really a desirable situation, but this is something that we can model. So you see, we have the initial deviation, and then we kind of go through the equilibrium to the original state 0 again. So it's not really now an equilibrium, it will turn out to be an equilibrium, fortunately. So we hit actually a little bit lower, if you like, or higher. So we get a bouncing effect from this underdamping. So the omega is still here taken to be 1. So we will see later what the role of the omega is. So what is the second what is actually the critical value? So this is what we could have considered earlier. So in the critical value, we have a very nice decay where as time goes by, so if time is expressed here in seconds, then in 10 seconds, the effect of the deviation is actually completely damped out. That's the critically damped. Then we have the over-damped. So in a way, by over-damping, we go more gradually towards the equilibrium state of the original state. And that's actually also if you want to have it in the opposite way. If you want to go faster, so if this is 10 seconds, you don't really like it. You like it that it's more closer to 2 seconds. Then here you see that by increasing the value of omega, that then you get a faster damping. So we have these two parameters, the zeta, that determines if you want a good damping, it better be 1 or higher. If you make it 1, you kind of have a different shape. You damp faster by the omega value. So these are the two important parameters, in this model of a suspension mechanism. Okay, so this is another model in mechanics. So one can see this a little bit. So we have an initial value problem. In numerical analysis, we consider boundary value problems. This is a little bit steering towards that. Although you can solve this by looking at the solution trajectory. So this is again, this can be done symbolically. So in a way, if you have not done any of the exercises yet in this chapter, please look into how to solve a differential equation and how then to plot a solution trajectory. So you can solve this problem with a plot. So you look where the plot, if you zoom in at the time frame, you can see how long approximately does it take before you are at 1% of your original deviation. And one can interpret this model also as a damping as a problem of damping. Okay, now let's do some mathematical biology. So last time we introduced the logistic equation to obtain a model for population growth. We are going to consider this model again, but now assume that there is a predator present. Here is the model as it was proposed in the 19th century. It's attributed to Verhulst. We have a population that evolves in time. The carrying capacity is capital K. So last time we derived the capital K by looking at the Taylor series for the right hand side. Here the carrying capacity is in the design of the right hand side. And of course we have the birth rate. So the birth rate is the first factor. So, but if we don't consider the carrying capacity, we have exponential growth, which is not really that realistic. So here you see that the rate at which the population changes depends on the birth rate times the size of the population. But then there is this factor that takes the carrying capacity into account. So this factor will get smaller and smaller as the population approaches its carrying capacity. So the rate of change can therefore declines steadily as the population size grows. So the purpose of the advantage of this model here is that one can predefine the carrying capacity of the population. So these are the two important parameters. So it is here shown. So we have the logistic growth for a particular numerical instance. With a birth rate of 0.78 as the initial population, and the carrying capacity is 50. So this is a nice numerical example without having any units attached to it, but any curve that will be used to model a population will have that kind of shape. So there is a steady growth, and towards the carrying capacity the growth decreases. So this logistic growth, by the way, has also been often used as the learning curve. So where the horizontal axis is the time spent studying, and the vertical axis is the amount that you learn by spending some time. So initially, in the initial phase, one expects to learn a lot, and then it tapers off as the time goes on. The more you know about the subject, the longer it takes to learn more about it. And the initial gradient determines somehow the difficulty of the subject. So one can use logistic growth to also model the growth of knowledge, not only population. Okay, so one can say that this model is probably not so realistic, because there is, if you look at biology, look at the animal world, there are always predators. So we consider here, so I took the model from the mathematical biology textbook, which I will cite in the end. So we have worms, and the worms have a natural predator, they get eaten by birds. So we want to study the evolution of the worm population. This may have a very practical, very practical purpose. I mean, because worms can do a lot of damage to a vegetation. So one may want to see if this, how large can this population ever get. Okay, so what do we do with our logistic model? We subtract a predator term. So the predator term is here the capital P. We used this in the previous lecture for the population size. So, and the predator term is a function of the population number. So, and one can even say that it is proportional in the sense that there should be enough worms um, in the habitat that we study. There should be enough worms already for the birds to start noticing. And once this happens, the bird starts to eat worms in greater numbers. So there is, as we will look at the steady states in this differential equation, we will have three critical values. And in the middle critical value, it's a very bad point for the worms because they are being noticed and they are being eaten. So let's look at what the predator term should be, what the shape of such a term could be. So here is the predator term. So it kind of models what happens in function of the n here. So n is the size of the population. So initially the predator term is very small because there are not many worms around and the birds simply don't notice them. Even at 10, when the size of the population, the number is 10, it's not really noticeable, but then it only picks up after 20 and it steadily increases and it starts to taper off the predator term after 30 and gets even smaller at 40. So you have this kind of shape that is growing slowly. So actually you do not want to have this as a model for a learning curve. But this is a curve which models the plausible effect of a predator correction term, depending on the size of the population. So there are two parameters in there, A and B, and I played with these parameters a little bit to look for a plausible plot. Okay, now comes some interesting symbolic computation. So if we look at the model that we have now, we have the birth rate and the carrying capacity as our two parameters. But now we have the two parameters A and B of the shape of the predator term. So 4 parameters, and that's a 4-dimensional problem. That's a little bit too much. So we will reformulate this problem to introduce what is called non-dimensional terms. So what we will do is we will try to factor out the A term so we can replace the capital N of time with A times a new variable U of time. So why is that? Well, then you look at the predator term. If you do that, then the A square appears in the numerator and it also appears again in the denominator. So the A square is going to disappear from the predator term. Okay, so we're going to have an A then at the left hand side. We have a B sitting in the predator term, and we want the B to be appearing also in what I call the growth term, the first term. So that's why the R gets replaced by B times R, and the carrying capacity is replaced by Q times A. So it's complicated, and it seems now that we are introducing yet another parameter. So we have 5 letters now. The Q has been added, but let's be patient a little bit. You can see here from the substitution. Perhaps I should have left out the focused on one substitution. But if you do the substitution going to the letter U, the function in time, then you can see that the A's will drop out. Okay, let's do the other substitution. If we do the other substitution, then you see that the B now appears at the left, and it will also appear at so the B appears in both terms here. So the A square is not yet cancelled. I probably should have removed it already. So it appears at the left. The B will appear when you do the derivative. Then the B over A with the chain rule will cancel the A, and the B will at the left and the right, and that can be cancelled. So then we replace, as the independent variable, we replace everything again by t. Okay, so now we have new differential equation which has the predator term in there but depends only on 2 parameters. Now the 2 parameters are related to the birth rate. So the birth rate, original birth rate, is at the right here, but the new R is actually a multiplication. It's a scaled form of the birth rate. The same with the carrying capacity. It's not the original carrying capacity, but it is the carrying capacity divided by A. Okay, now we have an equation that we can study. And I was mentioning earlier the critical parameters that we may expect when the population of the worms hits a certain size. Then the birds are starting to notice and will start to eat them. Okay, so let's look at the steady states. So the steady states are when the rate of change equals 0. So we then will see this right hand side as a purely algebraic equation. So I will replace the u of t by x. So we have now an equation in x. And observe that the x is a trivial factor. So in doing the substitution, there's a typo here. There is an x that is missing. So after the great bracket here, there should be an x. So where I'm here now with this hand. So in any case, you could also have seen it here. U of t equals 0 is actually a trivial factor. That's when the population size is 0. Not really interesting. Okay, so how can we see the steady state? So we can say that this is a root finding problem. It's actually more interesting to draw the curve of the right hand side. So here for the particular rate R and a particular Q value. So we have in blue the growth factor. So because of the carrying capacity, the growth rates. So these are rates. So it's not that the population goes down, but it as the growth rate goes down. Um, so, and Q equals 20, U equals 20. So you see this correction term at at U equals 20, there's no growth anymore because we are at the carrying capacity. Okay, so that's the nice evolution of this term of the growth with the carrying capacity. And then we had this nice shape of the predator term. So the predator term here makes this red curve, and there are three intersection points. So we may expect, and we will see, that there are three critical points. So there are three points, three equilibrium points. We call them steady states. So let's solve them. So we have a case where there are not too many, actually very little, worm population, so 0.4 or 0.5 if you like. That's the first equilibrium. Then we have the 2.4, which is kind of at the middle point. And then we have the case where there are many worms. So even in the presence of predators, the worm population is actually quite large. So 17. Okay, let's compute a solution. So we will take the parameters 0.4 and 20 for R and Q. The symbolic solver actually gave up on this, so we had to use the numerical solver. So good that we practiced this in the beginning of this lecture. So we have to define a function. So this is where we need to program something. We need to define the function that will be passed to the numerical solver that defines the right hand side. So we have the parameters sitting in there, 0.4 and 20. So here I didn't take it from the P. So it simply, they are the constants in the body of the function. Nevertheless, it's a one variable equation, but we have to work with U1 and du1. I tried to make it a little bit more readable by making special variables for the growth factor and for the predator term. Okay, so let's see what we get here with this model. So this is the evolution in time. So I started at 2.4 at time equals 0. So 2.4, if you remember, is very close to one of the steady states. So it's actually 2.43 then something. But as time evolves, you see that the population drops. And actually what happens is that it drops to the other equilibrium, 0.4. So as the birds are starting to notice the worms, they get eaten at a much faster rate than that they can recover. So the equilibrium 2.4 is actually not a stable equilibrium. Okay, there's something interesting that is happening with this. So I will describe what one can get out of the model. It's a good exercise to essentially compute more trajectories. So I started with 2.4, which is at the left of that unstable equilibrium. What happens if you start at the right? If you start at 2.5, do you then converge to the other equilibrium? Now, what happens if the birth rate increases? Then actually we have two steady states. Now they are still very far apart, 0.4 and 2.4. But as the birth rates will increase and the carrying capacity will remain the same, then actually the two initial steady states become closer and closer. So that means that if the growth rate grows, then actually you will get to, so instead of having only to, instead of having three equilibria, you will have only one equilibrium, and that's the one here where you have the large number of worms. So if the birth rate grows, then you get a catastrophic outbreak of the worm population. So you either go to the left or you go to the right from this unstable equilibrium. So now, if we would start with a high birth rate, then if we would go to a smaller birth rate, it will actually only possible when the large steady state actually joins. So the blue line here then needs to go much, much lower. So it's the middle point that needs to be joined with a larger point. So the unstable middle point in the first case, when the rate of growth increases, that joins with the smaller uh, steady state. So that's when the birth rate goes up. But when the birth rate goes down, so we are then at a large steady state, then actually before the worm population starts to decline, the middle, so you have to drag the blue line further down so that the two right steady states collapse and ultimately disappear. And this is then also where you notice a catastrophic decline in the worm population. So what I just tried to describe is that if the rate of growth increases, then at some point you have a catastrophic jump in your worm population. On the other hand, if the rate declines, so then we have also at some point a catastrophic change in the population, but it happens at a different value for the growth rate. So that notion, so we in the damping, we had a very nice transition with this zeta. Zeta 1 was the critical value, and we had two cases. But here we also have two cases. Either our budworm population explodes or it shrinks, but it happens for different values of the parameter. And actually it's depending of the direction of the change. And that is called hysteresis. Okay, so here is an example of a sudden change in perception. If we look at this picture from the left to the right, at the left we obviously recognize a face, and this turns into a shape, a different shape at the right. Now if we look at the same picture now from the right to the left, then at some point we will no longer see the shape that is at the right, but we will see the face again. Now the remarkable thing is, if you look from the left to the right, then it's only towards the fifth picture that you will see the shape. While if you look from the right to the left, you will see a lot longer the shape, and you will only start recognizing, I'm now saying what I'm experiencing, you will only see, say, this shape, you will only see the face in the third picture if you look from the right to the left. So that is a catastrophic event, but that also occurs at different spots. So this is a sudden change in the perception, but then it happens at a different place, depending whether you look from left to right or right to left. So this is the hysteresis illustrated. Okay, here is another specific model where we observe that if we look at the critical steady states, we can actually solve them symbolically, and they have this following parametric form. So in order to solve the first part of this exercise, so you can use symbolic computing, define the two expressions for R and Q in function of the symbol A, and then indeed verify that for A and Q, you have actually the non-zero steady states for these parameters. So solve the problem for specific values for which you have so it will be a specific value that's a cusp, and then interpret the solution when for which values of this letter A, what happens when the A goes to infinity. So you see that the R, the birth rate R, becomes actually very slow, very, very small. And you see that A equals 1 is also here a special value. Okay, so then that was an exercise. So here let's look at the proposal of a topic. So age plays an important role in the growth of a population. If you have an older population, then one can expect that the birth rate might not be that high compared to a younger population. And that's an important thing to consider. So for this project, you would need to read one section in the mathematical biology book that I used to prepare this lecture. This book is available online via our UIC library. So the point of this project is to make a computational model of this section. So work out the differential equations numerically and reproduce the plots that are very similar to that section. And then the question is really, what is now the effect of an aging population on its growth? At first one might think, can one just adjust the growth rates? But the model is more advanced than this. Okay, so summary. I'm almost up. So here in this lecture we combined symbolic and numerical computation to study models in mechanics and biology, models that use ordinary differential equations. So by now we are in the middle of our textbook chapter 9, and a large part of this lecture is actually based on mathematical biology. Okay, I have 1 minute left to switch to the Jupyter notebook. And that might be enough just to indicate a little bit what the problems were. So there were no problems in setting up the logistic growth. Here I point at the dictionary to formulate the initial condition. So one can solve this model in full symbolic generality. So if you like symbolic solutions, then here you see a solution that is symbolic and formal. So with the logistic model with the predator, so here you see the predator model again, there things got a little bit more interesting as far as the simplification go, or the rewriting of the differential equation. So far so good with the substitution here, but then in the transition to the non-dimensional terms, these substitutions needed to be executed. So here you see the simplify, which was so helpful in the previous lecture. Actually, it's not so helpful now. So when I do the substitution, so in my predator term, I want to cancel the a square, but I have to separate the arguments. So in this way, I learned something about symbolic computation. So I did the substitutions here, but then in the cancelling, I took the right hand side and then I took the arguments. So the new right hand side here was applying the cancel operation not to the entire expression, but only to one of the arguments. So the first argument. So here you see how the expression got simplified. The a square got cancelled, and then the left hand side, when you do there the simplification, that's actually kind of nice. So then we have a new symbol coming in, and the b is coming in there too at the left hand side. So you see in the equation, so we have at both left and both right the b factor that is sitting in there. And then all is well at the end. So I still need to do the division by b. I need to divide the arguments specifically, and that gives me then the new dimension, new right hand side, with the new terms for r and q. So we reduce the parameters from 4 parameters to 2 parameters. So this is where symbolic computation was extremely handy. Now the rest of the Jupyter notebook is very straightforward, and I'm running already over time, so I will not hold you up much longer. I hope that this lecture was interesting. So as I go back to the slides, the second reference is strongly recommended and could be a source for future projects in studying and using ordinary differential equations to model biology, evolutionary processes in biology. So thank you for watching.